Okay, cool. All right, so welcome everyone. My name is Ricardo. I work in CERN IT. I've been at CERN for quite a while by now. I will talk today about a slightly different topic or very different topic from what I just heard before, but there's some links as well. So I'll be talking about cloud infrastructure, cloud native, and as well as scientific computing, a bit of the evolution of what we had at CERN for scientific computing, and how the technology has evolved, and where we might be heading or not. So just quickly, I lead the platform's infrastructure in CERN IT for two areas. One is Kubernetes and containers. The other one is machine learning, which also covers like GPUs and accelerators. I'm also very active in the Cloud Native Computing Foundation, which I will talk a bit about it today. I'm part of what's called a technical oversight committee that kind of oversees the different projects in this area. There's a new body called the Technical Advisory Board, which is similar, but from an end-user perspective. And then we also formed, many years ago now, what's called the Research End-User Group, which is to try to push the use cases that are required for scientific computing into this kind of now ubiquitous infrastructure and platforms. So I will start with a little bit of history. I see some faces from CERN as well, but actually CERN, one of the characteristics of CERN from the start is that it always had big scientific computing requirements. When we go visit the data center or any of the experiments today, you will hear about petabytes of data. It will be even more for the next run in a couple of years. But this has always been kind of a trend at CERN. So I'll give a couple of examples. So starting with the 60s, we can see here the arrival of one very large machine, a CDC machine. You can see some of the specs here in the text, but what I would highlight here is from this article in the CERN Courier that says that the introduction of such a complex system was by no means trivial, and CERN experienced one of the most painful periods in its computing history. And this is kind of a trend when people start introducing new technologies, kind of disruptive technologies. There's always a learning curve, a lot of legacy systems that have to be migrated, things like this. So you will see that this can be a trend. So if we jump to a bit further, we can say another example with IBM with its MBS system. And it also says, describes a bit the other aspect, which was, it says, provided the opportunity for CERN to introduce Wilbur, the well-loved, cleverly designed, and friendly time-sharing system developed as Slack. And the reason I highlight this is that Slack is another laboratory that works very closely with CERN in Stanford. And this is also another trend, is that during the decades, this kind of requirements for a large amount of computing were very specific to some areas of business or in this case, research. It wasn't kind of everyone has needs to store petabytes and things like this. At the time, it wasn't petabytes, but large amounts of data. So there was a very close community between the different labs and centers that were working at this scale. And then, of course, in the 80s, we have the era of the supercomputers and the mainframes like Cray. In this case, I'm not that old, but actually when I arrived at CERN, there was one left still in the data center that was in a corner to be moved. But one thing I would highlight is that these were mainframes that require dedicated workloads and designs, but you can see also that it says here the decision was also taken to work together with Cray to pioneer Unix as an operating system. And this is, again, another characteristic of CERN is that it's very open into collaboration both with the industry and the communities, and to push the things that it thinks will be important for its future. And Unix is a very good example, because just a few years after, there was clearly a major shift. Actually, the project was called Shift, and there was even a library called libshift at the time. And there's a very nice article from Ben Siegel that is retired now, but you can still find him at CERN from time to time, where he explains this transition from mainframes to more commodity hardware and deployments. And this is something that really stuck into the not only the CERN culture, but the overall deployments of this kind of large-scale workloads. There's also some interesting things more towards the end that says the hottest thing in town with reduced instruction set, risk CPUs of a formidable 5 CERN units. And actually, people were managing computing capacity based on CERN units, which is also, again, an example of how CERN has been pushing this kind of large-scale needs quite extensively. There was also a very nice sentence that describes what was missing. So, for example, we saw before that CERN was collaborating to push Unix forward, but then it suddenly became clear that batch scheduling and the tape drive reservation system were features that were absolutely required and were missing in these systems that were available at the time to transition from mainframes. And you will see that history kind of repeats itself, and this is a bit of the trend. We change quite significantly the paradigm, but we kind of end up always having to add the special things we need that are not necessarily the main requirements from other kinds of use cases. And basically, the transition has been to what is still pretty much the look of our data center, but also kind of modern data centers, which is this racks with a large amount of individual computers. And then one thing that I would highlight is that some things didn't change that much. So we still use tape for large long-term storage, mostly for long-term storage and backups. But it's something that all the data is still going into tape. And if you are not from CERN, but you visit the shop, you can actually buy one of these tapes. They actually contain data from the LHC as we refurbish the tapes. There's always a prize for anyone that actually managed to read this data, and even a bigger prize if you actually understand the data that is inside. So if you manage this, you should reach out. All right, and then some 20 years ago, CERN also realized that there was no obvious way to get the funding and the setup to have one large data center in-house. The push was to distribute the capacity required for processing all the data from the LHC into multiple laboratories. And there were multiple reasons. They were not necessarily only technical, but this was the requirement. So there was a huge effort to build this very large distributed computing infrastructure that we called GRID. And several years of development for the different components you require, our own software stack. And this is what one of the important parts here is that at the time, there was really no push to do anything like this. If you look at today, you will think of the cloud, very similar kind of deployment. You will have multiple data centers across the world, but you don't necessarily know where you're running. You might know the region, but not necessarily the exact data centers, or in some cases, you don't even know the region. It just handles it transparently. And this is what the GRID, the purpose was all about, is to offer to the physicists and the researchers a gigantic batch system, where the data and the jobs are running is kind of not so relevant anymore for the physicists. And the system has the necessary logic to take these decisions of moving data to a certain place or deploying the computing where the data is or matchmaking other ways. The main thing is that it really took a lot of effort from us, but other institutions in Europe as well, in research, to actually develop these components. You need a workload management system. You need data storage systems. You need all the networking setup. All these components, all this middleware had to be developed by us and maintained long term. This is a massive effort. And the reason for that is because, again, we were kind of pioneering this kind of infrastructure. Now, if you look at the scale of things that we require, this is actually a pretty old screenshot, but you can see that at any moment you will have something like 400,000 jobs running on this infrastructure. In total, It offers over 1 million CPU cores, which by modern cloud data centers is probably not that big anymore, but it's still extremely significant for one single use case. But then it all got cloudy, and this brought really good things. Suddenly, there was an interest to look at offering this capacity, which was kind of the dream of the grid, to offer capacity the same way we get electricity. You would just plug in your laptop and get extra capacity from whatever the grid would offer. And the cloud kind of built on this, but in a more organized way, I would say. Instead of the more chaotic grid where anyone can plug in their own resources in more or less well-managed fashion, the cloud is really an offering which offers the stability and reliability that people would expect. And this opened a lot of options for many companies. Suddenly, everyone had access in a quite easy way to a huge amount of computing capacity. So everyone started doing big data. Like everyone was collecting a lot of data, but there was no easy way to actually make any kind of money out of this data. With the cloud, you could actually pay without having to build your own teams, your own infrastructure. You just pay for the resources on demand, and this opened a lot of opportunities. So Amazon pioneered this, or others pioneered, but Amazon kind of made it mainstream around 2006, and others jumped in, and it got really, really popular. So for sure, everyone here has used the cloud before. You can see the main ones like AWS, Azure, Google Cloud, Oracle Cloud, IBM Cloud, then some other public cloud vendors or providers like Exascale in Switzerland, OVH. And then, of course, there was an interest to have communities and open source products that would offer you the possibility of having the same kind of infrastructure managed on premises. And this is where products like OpenNebula, CloudStack, and OpenStack that we use extensively here at CERN became popular. There was one clear issue, is that all these offerings have proprietary APIs. So there was no benefit, especially for AWS, that was the major provider, to actually open this. Lock-in is a thing in the public cloud. They will try to lock you in either with APIs or making data extremely expensive to move around. So there was in the community a sense that this has to be broken. And this is where this movement for cloud-native infrastructure came in. And there was a need to host all this movement. So one of the big pushes came from Google. And they created Kubernetes, which I'm guessing everyone has heard of. And they actually donated the Kubernetes project to a foundation to make it vendor neutral in a way that everyone would jump in. And really, the main goal was to go get some market from the main provider at the time. But everyone benefits, so there's quite a lot of advantages. So we really went from developing our stack. If you think of what I mentioned about the grid, all these components, I came to CERN as a software developer. I've converted to being what we call DevOps, but it's basically just building stacks out of existing components and putting glue here and there. So I do very little development these days, and there is a trend for the profile in places like IT at CERN, but also elsewhere that work on infrastructure to do exactly this. There's a lot of people working on the upstream projects, but the large majority are actually managing these stacks. So the Cloud Native Foundation came up. This is a foundation that has as a mission to make Cloud Native ubiquitous, like they claim here. There are things that are quite important, which is this should be loosely coupled systems that are resilient, manageable, and observable. This is really the definition of the cloud. You don't want to have pets, you want to have cattle in all senses, so that things can recover automatically and they can suffer outages without causing any kind of major downtime. So the foundation started with one project, which was Kubernetes, but it got quite popular. So it started building this notion of maturity levels. And I will show you how large this thing has become. But one thing that was pretty obvious from the start is that you need to be able to adopt new projects, but then you have to help those projects mature. And there are many characteristics, like when we talk about open source, and I saw that one of my colleagues talked about open source this morning as well. An open source project, you might say, if the source is open, then the project is open. This is not the case. Like, having the source open is just one small step. You need to have a clear governance on who actually is maintaining the project and making the decisions on roadmap and accepting merge requests. You need to have a way for people that are contributing the code to evolve in their roles in the project, to become maintainers and also have a higher contribution. And you need to have vendor neutrality so that anyone that wants to make money out of this project, and you need someone to make money, otherwise it's very hard to make this project sustainable, that they can have the confidence that if they need to make changes to the project, they can actually do it. And the same is true for IP policies and many other aspects. So the code is just one part of the open that is required. So in the CNCF, the structure has been that there's this idea of sandbox projects. The sandbox projects are kind of where people are innovating and experimenting. And there are many cases, I will show a couple. You want to expose this to more people, to have more visibility, and then build a community and grow as a project. And then once this community is established, you move into this incubating, which is where already some due diligence has been made. So we already verified that a lot of these items that I was talking about are being implemented, but also that the adoption matches what you expect. You need some users, you need some production deployments. And then gradually you move to higher levels, like graduated levels. The foundation grew quite aggressively. This is extremely popular as an ecosystem. So you can see from February 2016, which is just after Kubernetes was integrated, it's been growing quite rapidly. You see now over 200 projects, or just under 200 projects if you exclude the archived ones. You can also see the number of projects that are being accepted into the foundation. There's a review process, so not everyone that wants to join is able to join. There has to be some alignment with the rest of the ecosystem. And the last plot I have is the movement of the projects between levels. So the goal is really to help the projects move towards graduation. Now, this is how it looks today. So it's complete chaos. This is what's called the landscape. It's used as a joke, usually. But this is the reality of this ecosystem. Of course, not all these projects are usable for the level of stability that people might require. So, for example, if you catch a sandbox project here, it means that internally you'll probably have to do your own due diligence to see if it fits your use case, if it's stable, if it has a community, if it's sustainable in the future. But if you take an incubation project, you can already trust that a lot of this work was done by people in the technical committee. And if it's a graduated project, it's pretty much guaranteed that you can have a sustainable project at least for a few years ahead. But this is what has been built in the last few years. But around 2019 at CERN, we wanted to demonstrate or experiment that this is actually something that is useful for us. So what we tried to do, and we had a nice occasion to do this at a keynote of a large conference, we wanted to reproduce the Higgs discovery. It's kind of a stunt. If you're a physicist, don't get offended. But what we wanted to do was do kind of a stunt of reproducing the analysis that was done back in 2012 in 2019 and see how much faster and how easy it was to do with this new kind of stack. So what we did is we took the software that was used in 2012, which is actually software that is much older than that. In the previous talk, there was some mention of, I don't know if someone did Fortran. There's a lot of Fortran in that software. So, but the idea was that you containerize the analysis that could trigger the discovery of this particle. You wrap it up, and then you put all the software that is required there, you put it in a registry. I'm sure everyone has used containers. And then you try to deploy this in a totally different infrastructure, which is managed by Kubernetes, cloud-native tools. And we tried two things. One was to run it on premises, and the second one was to run it on a public cloud. And we wanted to evaluate how possible it is to reproduce this and make a reproducible analysis in a totally different system. And then how easy it is to move from an on-premises to a public cloud. This was the promise that all these tools were giving us. So we started with CERN, and what we had to do was analyze a 70 terabyte data set. The issue we had is that this keynote was quite short, and we only had 5 minutes to do the analysis. So we saw that we needed 30,000 cores to be able to produce, to analyze this 70 terabyte data set in 5 minutes. So we asked for 30,000 cores at CERN, and they said no. That was pretty clear. But we could experiment with it. So we could run the 70 terabyte analysis using a Ceph backend, and then a Kubernetes cluster in our infrastructure that at the time, I don't remember anymore exactly, but it had a couple of thousand cores, but nowhere close to the 30,000 we needed. And then we were using Redis for storage and Jupyter for the visualization. This took around 8 hours to run. The initial analysis was over a day. It took 8 hours because we couldn't expand the cluster. But we needed 5 minutes, so we needed to scale this significantly. So we asked the Google Cloud, and we had some friends there, so we asked, can we get some credits? So they gave us credits, and we got credits to run 25,000 cores. And then we actually had to learn quite a bit about public clouds and how they work, but we could deploy a single cluster with 25,000 cores, run 25,000 jobs in parallel, one per core, store the job results in the Google Cloud equivalent of Redis, and then analyze the results. The core here is, of course, the Kubernetes cluster, because it's what gives us the API to transition one workload from one place to the other. Apart from the details of transferring data, the actual workload submission was pretty transparent. And this is what we needed. We needed like 5 minutes to create 25,000 core cluster. We needed 4 minutes to pull the image, and I will come to this after, but we could do this previously to the analysis. And then during the actual keynote, we were just staging in the data from the Google systems into the nodes, the 70 terabytes, into the different nodes in the cluster, and then the analysis was 90 seconds. So we could actually shorten, in 7 years, from 2012 to 2019, scale out using public cloud resources and very little infrastructure knowledge, from what took a day to 5 minutes, which is quite spectacular if you think about it was a totally different infrastructure. So this was quite positive. We actually did this live. We also played visualizations. So every time some of the Higgs events were, or some of the events were being analyzed, the plot was being built live. So at some point you can see the blue part, which is the simulation data matching these crosses, which are the real raw data coming from the data sets. So this was quite nice, and it was a stunt, but it proved a point, and this was the main purpose of the whole exercise. What we also learned is that this notion of reproducibility that has been quite pushed about data, that you need to publish your articles with the data. We also saw that you actually need to publish also with the software. And using containers opened up this possibility of really having single blocks and units that you can share along with the data with your colleagues or with your scientific publications. And this is something that there was a publication in Nature about reproducibility and open science, and this was one of the things that was highlighted there. So I will have a couple of examples and demos to kind of show you where these things are actually having an impact. The first one I will mention is software distribution. So you can see here, when you look at this image, it's kind of depressing that pulling the software is actually such a large fraction of what we are trying to optimize in terms of overall analysis. So I will ask a question. Who has used containers? pretty much everyone. Who has used an image? So we all know container images should be optimized and small. Who has had to deal with an image that is 100 megabytes or bigger? Or let's start with 10 megabytes or bigger. 100, 1 gigabyte, 10 gigabytes. Still people, I'm really sorry for you. So I'll continue, 20 gigabytes. No? Okay. So this image that we used here is 18 gigabytes. And there are many reasons that this can happen. Ideally, you should have layers, you should reuse everything. But when you have a full CI infrastructure building software releases, it's really hard to change these things and make these ideal images. So actually, we looked into an alternative, which is instead of fixing the users, we fixed the tools. And one of the bad parts, but good parts, one of the very good parts of containers is that they are layered. One of the very bad parts of containers is that they are layered. So here you can see that actually layers in a container are just tarbles in reality underneath. Now there was someone very smart at Google at the time that came up with this concept that a tarball of tarbles is actually a valid tarball. And when you do a tarball of tarballs, you can put some metadata that makes it a seekable tarball. So what he came up with was this idea that inside a tarball, you put tarballs with every single individual file being a tarball on itself. And then you put some seekable metadata, which means that when you contact a registry, you can ask for the exact file you're interested instead of pulling the full layers of the image. So the idea is exactly this, is that you go to an image, you convert it into this star.gz format, and then you just start the workload immediately, and you just mount remotely the image. And the container will start immediately, and then as the container asks for this file, the responsible for pulling the actual image content from the local file system will instead pull the exact file that is required from the remote registry. So the result of this is that you can actually have, instead of pulling images, you can access individual files. And there are some statistics. There's a very nice blog post from the team that actually shows that on average, only 6% of an image is actually used for this kind of images. And this is exactly what we also measured. So you can see that the potential performance improvements are pretty large in terms of both the speed to pull the image and to start the workload, but also the network load that you put. Because if you have a cluster with 1,000 nodes, each pulling a 20 gigabyte image, it's a pretty good way to do a denial of service of your registry and bring down the network. We've done it many times. So another option is to try to do something like this. So I'll show you in this case. I'll do just a quick demo. So you can see here that I have a cluster that has 6 nodes, 1 master, and a bunch of workers. These 2 workers are not star.gz enabled, so they will try to pull the full image. And these nodes are star.gz enabled, so they will do this functionality that is called lazy pulling usually. Now I will use an image just because we can. This is an actual production image. If you're using FPGAs, you've heard of Vivado. This software is packed nicely into 90 gigabytes and sometimes 100 gigabyte images. And this is not the worst case I've seen, so it can get worse. So what I will do, I will apply this. I will start with a non-star.gz, and you can see here that the container is creating. Now what it will try to do is pull the full image, the 90 gigabyte image, into the node. The problem is that in this cluster, I gave the nodes only 20 gigabytes of space. So obviously, this will never work. And this is a common event, is that you fill up the node, and then when you pull the images, if they are large, they will just fail. So if we try to access what the job is doing, or the pod, you can see that it's trying to pull the image. It's taking a while because it's trying to go for it. And you can see here that it already errored. And if I describe it again, you will see that the message that it's saying is that there's no space left on device. So it's basically impossible to pull. So what we'll try to do is instead, we'll use a variation of the image that is actually star.gz. It's the same image, but in an star.gz node. And you can see that in this case, if you're familiar with Kubernetes, the only thing that I'm doing is that I'm adding what's called a toleration so that it can be deployed in these nodes that are specially configured. So I will apply that one. And you will see another one now running in one of these other nodes that has this capability. And it takes a little bit of time to kind of do the pod start, but it's already running. And obviously, it didn't pull 90 gigabytes just now. It's just it doesn't have the capacity. And again, the node has 20 gigabytes, so this would be impossible. What's happening is that when the workload will actually request the files, it will be pulling exactly only what is required. This is the first demo I have. I have a few. So the second one is, this is a thing that came from the beginning of Kubernetes and Cloud Native, which is, it was about containers. But if you remember the description I made of the Cloud Native Foundation, it actually talks about a lot more things. It talks about microservices, which you associate with containers, but it talks about a lot of other kind of workloads. So people started realizing that Kubernetes is actually an excellent way to manage the lifecycle of whatever. And there's a notion of a custom resource definition where you can extend Kubernetes with your own things. So people started doing this. And there are projects like KubeVirt that actually manage virtual machines using libvirt underneath with Kubernetes. And there's projects like Crossplane, which are pretty smart. And they basically wrap all the functionality that the cloud provider would give you, like creating Lambda functions, objects, whatever. And they will wrap it in Kubernetes resources. So then you can manage them as if they would be Kubernetes resources, which means if you're using tools like Argo or Flux, all the GitOps thing on top, you can just reuse to manage your VMs, your networks on the cloud, any kind of load balancers, any kind of thing that you require. So I'll try to demo that as well. And I will show you this by creating a VM in our OpenStack instance. So this is just a cluster that I created. That basically has Crossplane installed. And in this case, I will try to create, if you know Kubernetes, it's all YAML. So in this case, I'm creating a type of resource that is called instance, which is OpenStack instance in this case. And you could have providers for GCP, Azure, whatever. And then I tell it the flavor I want to use, the image I want for my node, the key pair, and the network I want to associate it with. So I already created one before. You can see it's created here. The VM is running. And this is the one that I created here. You can see it looks like this. It's called VM10. And if I list the servers in my tenant, I can see that the VM is running there. And you can have some feedback saying if the VM is ready to be used, or if it's already synced the resource and things like this. So you can see here, you can also see the IP address. If I do a describe of the resource in my Kubernetes cluster, sorry, oops. So you will see that all the metadata that you have on your OpenStack, you would have here as well, like the IP, whatever. So you can use this for any kind of workload. So what I will do is I will create another one. So I'll create another one that we'll call 20. And you can see that immediately the VM is being created. It says here that it's already synced, which means if I list it here, I will see a second VM that will be in build state because it's about to be deployed. But as far as I'm as a Kubernetes user, I don't care. It could be a VM in OpenStack. If my admin of my cluster would change it to GCP, that's it. So it's all kind of abstracted into these concepts. The same is true if I try to delete a resource. So if I delete the initial VM I had, so this will try to delete this one. You will see that ready went to false, and now it's syncing because it could take a while for the VM to actually be synced on the OpenStack side. But it becomes really easy to manage any kind of resource, so it's already gone, you can see there. And that's demo number 2. The same thing we use, for example, when we manage clusters across multiple cloud providers, we manage the clusters themselves as resources in Kubernetes. The third one is batch. So I mentioned when we did the transition to Unix, there was a batch functionality missing, like advanced scheduling, things like gang scheduling, co-scheduling, priorities, queues, things like this. And this was exactly the same when we started using Kubernetes. Like Kubernetes has the notion of a job, but it's not what we want. It's more like the Hadoop kind of MapReduce type job. It's not really what we understand as batch, and there was no way to do queuing or co-scheduling or anything like this. So some projects appeared, like Volcano, Armada, which were at different levels of usage. Some of these projects, like Volcano, are used in places in Europe and the US, but then you go to China, because it's mostly a Chinese community project, and you hear about clusters with 90,000 GPUs being managed by tools like this. Armada was also created by a financial institution. The one that I will focus on is a project called Q, which is basically trying to add this functionality on core Kubernetes. And this is quite important because it ensures the sustainability that we require. And it means that very easily we can rely on this on premises, but use on public clouds as well. So I'll try to demo this as well. I have here a very basic explanation of how this works. So you create your queues, and then each queue has flavors. You can have different types of flavors in the cluster, and then you associate clusters with flavors with clusters. A flavor would be like, I don't know, ARM or AMD 64 or GPUs or whatever special thing. And then each node has these capabilities offered. But then you can have your own queues, and you kind of have a separation between what the user queues and the actual admin queues are. But I will not go too much into that. What I will show you is a very simple example of how this works. So here I have a cluster with queue running. I will try to submit a few jobs. I will submit the first one, and you can see that it's already running. I'll submit the second one, and you can see it's running. And these jobs are pretty simple. All they are doing is basically just sleeping. But they do ask for 1 CPU each. So this cluster only has capacity for 2 CPUs because I want to do a demo. So what I will do is I will submit another job, and you will see that the third one is actually suspended. And this is something that you wouldn't be able to do without queue, because the job would just fail. Like there's no capacity. The system would constantly be trying to run it and constantly failing. So you're not queuing your workloads. So what we can do instead is deploy queue. It will go into suspending mode, and once one of the other ones finishes, it would make space. But it also allows you to do something like this, which is I will show you a high priority job, and all you have to do is define a different priority class. I define 2, 1 low, 1 high, which means we can actually try to deploy now the high priority. Sorry. Whoops. Yeah, so I'll apply the high, and you can see here one of the jobs is suspended, the other 2 are running, the low ones. I will deploy the high, and what will happen, what will happen is that another job of the already running ones went it suspended so that it makes space for the high priority workload. So we basically have a batch system available on premises because we have Kubernetes here, and on any public cloud provider because they all offer you the capabilities to do Kubernetes. Now I have one last demo, which is this on steroids, which is instead of doing only one cluster, we'll try to do multiple clusters. And this is kind of this idea of the grid, that you have this many sites all seen as a single batch system. So I'll try to show you this here. I have a pre-set up cluster which has a management cluster and then has 2 clusters, one here in the data center at CERN and one in a public cloud provider. And then I set a few queues, one for local jobs here, and then another one that submits workloads externally. So what I will try to do is show you here that these queues are here. We have a local, which we will not use, but we will use this multi-queue on premises and then multi-queue external. And I can show you also that we have 2 clusters that are workers, one on premises and one external in a public cloud. And here in this, you see the management cluster where we'll track all the jobs. This one will be the on-premises cluster, so we'll see some of the jobs here, and this is the remote cluster. So I'll very quickly try to run this demo, which is I will start by creating an on-premises workload, and it's created in our management cluster. But you see that it's actually not running in this cluster. It's in suspended mode, and the actual workload is running on a remote in another cluster, which in this case is also on premises. You can see it's pretty quick. I have a single control plane. I can manage all the jobs in one place, but actually the workloads can be running, and I can define the policies of where the workloads go. So I can create a couple of more, just to show you, and it's quite quick. I can also delete one to show you. I'll delete one of the recent ones. So if I delete a job, again, I'm only talking to the management cluster, and you will see that it disappears also in the remote cluster pretty quick. So this is really, really neat. Now, what I will try next is to create a similar job, but in this case, I'm using an external. I'm saying that I want to use another queue, which is the one that is configured to deploy to a remote cluster. So in this case, I will create this one. And you will see that the job still appears here in my management cluster, but actually it took a little bit longer because the latency is higher. But the job is now running on a remote cluster, in this case in a public cloud region in Germany. But still, I have all my jobs here. I can monitor it easily. Now, the last one I will do is I will deploy a similar one, but with GPUs. And this is just to demo how quickly we can do changes. So in this case, I'm deploying a job with a GPU, and you can see that it's running nowhere. And the reason for this is because I haven't configured my queues with GPUs. So what I will do is I will try to do this live here. This is a production cluster, actually, but just for the demo purposes. Why not? So I will try to reconfigure my cluster. And if I get the indenting right is even better. Looks correct. I will also add a local queue. And I will push to master, as you do in live demos. And what should happen is that we will see a new queue here appearing soon. All right, we have the queue appearing. So this is, again, the magic of GitOps, because I just pushed to Git. The clusters reconfigure themselves. In this case, it was actually reconfiguring a remote cluster, and you can see now the GPU workload running since 7 seconds. So it's really, really neat. I can have a central plane configuring a bunch of clusters across multiple parts of the world. And basically, that's what I wanted to show you, is that we had all these transitions of paradigms. We are currently going through this cloud-native transition. We started with managing services and doing a lot with Kubernetes, but we are actually now pushing to do this also at large scale for scientific computing. Containers give us this improved reproducibility that I mentioned. We're really becoming more like builders and stackers than actual developers in this area. And we have to focus a lot less on infrastructure, which leaves us more time to focus on the science part. And one good aspect is that it actually democratizes science, because everyone has the capability now. You need a credit card, but still it's, in terms of the setup, you can get access to a large amount of resources, which opens the possibility for a lot more people to work on science, especially with the open data. And that's all I have. Happy to answer questions. Yep, I don't know. I go over there.
This suspension, is it graceful? Does it send any signal so process can finish network or something?
That's a very good question. So this preemption, when the job is preempted, there are multiple preemption modes. It can be that it never allows a job to be preempted. It can be that it can be immediate, or it can be that it has to be graceful in the term of sending like a SIG abort or something like that, so that the job could checkpoint and then later be restored. You can also give it like a time window. You can give it 10 minutes to checkpoint and restore, and then you actually kill it. Yeah, so this is configurable. There's another one just behind.
You mentioned, well, the control plane. Do you know what the overhead is, in the sense that how many machines actually running Kubernetes and not the jobs?
So just for the metadata management, you mean, for the jobs, or for
In general, for the whole cluster.
Right, so the worker clusters really need the resources to actually do the computation. So it's whatever the job is. The overhead is in the management cluster, because if you start having like thousands or tens of thousands or hundreds of thousands of jobs, you need to kind of deal with this metadata, and these queries have to be pretty quick. So this has been solved in Kubernetes in single cluster deployments. The largest deployments can handle easily hundreds of thousands or millions of individual resources in a tool, in a component that's called etcd, which is basically key value store, and you can scale out the etcd deployments. So this has been tested widely. Then for the worker clusters, the idea of multi-queue is really to spread in multiple clusters, but even if you would want very large individual clusters, the largest cluster I know of is 65,000 nodes. And this is managed by public cloud providers. From end users, people that actually run on-premises deployments, I know of clusters with 5,000 nodes as well.
Do you know how many of those nodes are then actually used for management only?
On a 5,000 node cluster, it's not really related to the size of the cluster. Actually, managing 5,000 nodes is not a big problem. It's managing the number of individual resources that is the problem. And I would say, like out in thin air, but there are numbers about this. But if you have like 100,000 resources, you would need probably 5 etcd nodes of like a decent size. I would say maybe 32 cores, half a terabyte of memory, something like that.
Thank you.
Yeah, and I think we're out of time. So thank you very much again.